This is 3.2.1 part 2. We'll start with Young's double slit experiment. Now to conduct this experiment, we're going to use a laser. Then we've got a double slit with a slit separation of about 0.5 millimeter. And we have a screen on the far side. The separation from the slits to the screen is called the screen distance. Given by D. That 0.5 millimeters here is called the slit separation, given by S. And on the screen, we get an interference pattern with fringes forming. And these fringes are separated by a distance called the fringe width. W. This one here is your central fringe. The path difference for the central fringe is equal to 0 lambda. So as we go up to each next fringe, the path difference will go up 1 lambda, 2 lambda, etc. And the gaps in between, so the dark spaces, those are going to be n plus 1/2 lambda. Yeah, so the spaces in between will be 1/2 lambda, 3/2 lambda, etc. That's both true for going up and going down. So this one here will be 1 lambda, 2 lambda. Down here will also be 1 lambda, 2 lambda, etc. Now, the equation, we'll just put some numbers here. The equation which relates these together is W equals to d lambda over S. So W is our fringe width. Measured in meters. D is our screen distance. Also measured in meters. Lambda is our wavelength. Also measured in meters. And S is the slit separation. Also measured in meters. So an example question. A physics teacher wants the fringes further apart. How could this be done? So to answer this question, you need to consider the equation and analyze the equation. So, if you want the fringe width further apart, when you look at the equation, you can see that the fringe width is proportional to the screen distance. It's proportional to the wavelength of the laser. and it's inversely proportional to the slit separation. So you have three ways of doing this. First is to increase the screen distance. So move it further away. Second is to use a longer wavelength laser. So if they were using a green laser originally, then they would have to use a red laser which has a longer wavelength after. And then the last one is to decrease the slit separation. Now, if we were to look at the screen head on, so we're looking at the plane of the screen, we would see the fringes in a different manner to how I plotted earlier. And according to the fringes, we can plot an intensity graph. And this is for two sources or two slits. So what we see is our bright fringes and dark. And the intensity graph for that would look like this. I've tried to line them up as good as possible, as much as I could. So there is a clear difference between single slit diffraction and a double slit. In a single slit diffraction, you get what is called a single slit diffraction pattern, also known as an airy disk. You have a very bright central maxima, and all other maxima after the central bright one decay very quickly. With the interference pattern, the other fringes have maxima that are approximately or comparable to the central bright one. Now they do eventually decay as well, but they don't decay as quickly as the single slit diffraction. Let's turn a page here. Now we can see this with microwaves. So if we had a microwave transmitter and we placed a double slit in front of it, and we took a diode detector and we moved it down. I think I'd rather move the label here. As we move it down, if I were to record on the side a graph of how the intensity looks like as we shift that diode detector down, we get a graph that looks very similar. So as we're moving down, this is how the graph will change. And on this axis, we've got the intensity. So think about microwave ovens, right? They have turntables in them, which turns food around while they're being cooked. Now, without that, you see that there are spots where you have minima. So if you had food in a microwave oven that was not being rotated, the spots that correspond to where the minima lie will not heat up because they will not absorb any energy. The same can be seen as well if you had two speakers. So this is now the longitudinal wave. So if you had two speakers that were playing the same tone, and you took a microphone and you moved it down, this would also produce an interference pattern. And that's why, when it comes to audio, there is what's called the ideal listening position. So in, for example, a home theater setup, a company who is building one of those would figure out where the ideal sitting location is compared to the separation of speakers in order to not have the person who's watching the movie or people watching the movie sitting at one of the minimas, because there will be a discernible difference in the audio if they did. That's the end of 3.2.1.